Good evening and welcome everybody. It's Obi-Wan Pez for N-Simplex Pachinko. We're going to be doing some math a night late, but whatever, it's all good. Thought I would belate my Math Communication Monday, but then still do it, so. Alright, so today I was listening to the old Steven Strogat's podcast, The Joy of X, and on it he had a professor from University of San Francisco, or San Francisco. Oh dear. One of those anyway. Yeah, San Francisco State University. There we go. Federico Ardila, who is from Colombia, and he was talking about specifically combinatorics. This is in 2018, I want to say. He was on Steven Strogat's podcast. It might have been 2021. And talking specifically about combinatorics and trying to teach him a little bit about combinatorics, because apparently Steven Strogatz did not have to take combinatorics. I find that kind of wild. And I believe it was on this algebraic and geometric methods in enumerative combinatorics. So I thought we would take a look at this one in particular. And then I found it when I was taking all my stuff out of these boxes. Mathematicians' Attitudes Toward Computer Proofs by Ken Appel. So I thought we would also go through that one because it's Ken Appel. He did a single lecture for my mathematics history class in 2003, I want to say. So I thought we'd go over that and take a look at that particular. Take a look at that particular paper. This is a paper that was based on talks that he gave in Spain in 2003. So must have been fall 2003 that he came over. I suppose spring 2004 would be just as acceptable, but okay. So we're going to take a look at algebraic and geometric methods in enumerative combinatorics. PDF from arXiv. You punks. Okay, well, guess we'll just be going over there. Jeez. Okay. Introduction. Enumerative combinatorics is about counting. The typical question is to find the number of objects with a given set of properties. However, enumerative combinatorics is not just about counting. In real life, when we talk about counting, we imagine lining up a set of objects and counting them off, 1, 2, 3, etc. However, families of combinatorial objects do not come to us in natural linear order. To give a very simple example, we do not count the squares in an m by n rectangular grid linearly. Really? I don't know what is going on. Like I restarted my computer earlier. Shared processing stuff is off. Let's check real quick. Like Firefox is taking up a substantial chunk of virtual memory, it looks like, but whose main thread? Well, that was not helpful. Oh well. Anyway, instead we use the rectangular structure to understand that the number of squares is m times n. Similar to count a more complicated combinatorial set, we usually spend most of our efforts understanding the underlying structure of the individual objects or the set itself. Many combinatorial objects of interest have a rich and interesting algebraic or geometric structure, which often becomes a very powerful tool toward their enumeration. In fact, there are many families of objects that we only know how to count using these tools. This chapter highlights some key aspects of the rich interplay between algebra, discrete geometry, and combinatorics with an eye toward enumeration. See, this is way more my speed. About this survey, over the last 50 years, combinatorics has undergone a radical transformation. Not too long ago, combinatorics mostly consisted of ad hoc methods and clever solutions to problems that were fairly isolated from the rest of mathematics. It has since grown into a central area of mathematics, largely thanks to the discovery of deep connections to other fields. Combinatorics has become an essential tool in many disciplines. Conversely, even though ingenious methods and clever new ideas still abound, there is now a powerful, extensive toolkit of algebraic, geometric, topological, and analytic techniques that can be applied to combinatorial problems. It is possible to give a meaningful summary of the many facets of algebraic and geometric combinatorics in a write-up of this length, 144 pages. I don't think we're covering it all. Just, you know. I found it very difficult but necessary to omit several beautiful, important directions. In the spirit of a handbook of enumerative combinatorics, my guiding principle was to focus on the algebraic and geometric techniques that are useful towards the solution of enumerative problems. The main goal of this chapter is to clearly state clearly and concisely some of the most useful tools in algebraic and geometric enumeration, to give many examples that quickly and concretely illustrate how to put these tools to use. His footnote is that he was or is currently, well, at time of publication, was working at San Francisco State University, San Francisco, had been at Universidad de los Andes in Bogota, Colombia, or maybe he has support from there. close to final draft of Chapter 1 of the upcoming Handbook of Enumerative Combinatorics, February 2015. Please refer to the book for the final version. Just out of curiosity. Whew. All right, that's a textbook. Looks like you can get it from Routledge. There's a PDF right there. But otherwise, the Handbook of Enumerative Combinatorics is on eBay for multiple different prices. However, starting at £130 and going up to £235. Whew. Aha. Yep. So chapter 1 looks like it's here. Oops. Algebraic and geometric methods in enumerative combinatorics. Big, giant, copyrighted material, Taylor and Francis going across it there. And this is just the first 20 pages. Good times. Sorry. Tom Scott. Right. I mean, this looks more than just a chapter. This looks like almost the entire book. Hang on, wait, this has... Oops. This has... same chapter headings. Yeah, okay. Yep, that is, roughly speaking, the first chapter. 1.8, 1.8.10 up to page 155. Nah. Right. First part of this chapter focuses on algebraic methods in enumeration. Section 1.2 discusses the question, what is a good answer to an enumerative problem? Generating functions are the most powerful tool to unify the different kinds of answers that interest us: explicit formulas, recurrences, asymptotic formulas, and generating functions. Section 1.3 would develop algebraic theory of generating functions. Various natural operations on combinatorial families of objects correspond to simple algebraic operations on their generating functions, and this allows us to count many families of interest. In section 1.4, we show how many problems in combinatorics can be rephrased in terms of linear algebra and reduced to the problem of computing determinants. As always, the mathematician's job is to reduce the problem to one that has already been solved. And finally, section 1.5 is devoted to the theory of posits. Many combinatorial sets have a natural posit structure, and this general theory is very helpful in enumerating such sets. So section 1.2, what is a good answer? The main goal of enumerative... Yep, it is. Hey, Stuki, how you doing? Yep, Federico Ardila. I just listened to his guest appearance on... So yeah, just listened to his appearance on The Joy of X, probably from 2021-ish, and thought it'd be interesting to see if I could look up some of the stuff he did. So this looks great. I ended up taking combinatorics as part of the curriculum at Johns Hopkins University, and combinatorics was one of those classes that just really clicked for me. I think probably like trying to find some sort of function given a bunch of data or a bunch of constraints was kind of like what I really liked doing. And I'm pretty sure it was combinatorics where after I got the homework assignment, my spouse and I drove to a Cold Stone, and while we were waiting in the very long line, I ended up doing like half of the first homework set, just like standing. I mean, yes, it was easy because it was the first homework set, but also like I was just engrossed in it. I loved it. The class as a whole went pretty well, all things considered. So what is a good answer? The main goal of enumerative combinatorics is to count the elements of a finite set. More frequently, we encounter a family of sets T0, T1, T2, T3, etc., and need to find the number T sub n, which equals absolute value of big T sub n for n equals 1, 2, etc. What constitutes a good answer? Some answers are obviously good. For example, for the number of subsets of 1, 2, etc. to n is 2 to the n, and it seems clear... Oh, the number of subsets, yeah. And it seems clear that this is the simplest possible answer to this question. Sometimes an answer is so messy and long, quote, so messy and long, and so full of factorials and sign alterations and whatnot, that we may feel that the disease was preferable to the cure. Citation 218, okay. Usually the situation is somewhere in between, and it takes some experience to recognize a good answer. A combinatorial problem often has several kinds of answers. Which answer is better depends on what one is trying to accomplish. Perhaps this is best illustrated with an example. Let us count the number a sub n of domino tilings of a 2 by n rectangle into 2 by 1 rectangles. There are several different ways of answering this question. Explicit formula 1. We look for an explicit combinatorial formula for a sub n. To do that, we play a few simple examples and quickly notice that the tilings are structurally very simple. They are just a sequence of 2x1 vertical tiles and 2x2 blocks covered by 2 horizontal tiles. Therefore, constructing a tiling is the same as writing n as an ordered sum of 1s and 2s. For example, the tilings of figure 1.1 correspond respectively to 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 2 plus 1, 2 plus 1 plus 1, and 2 plus 2. 1 plus 1 plus 2 plus 1. Not 1 plus 2 plus 1 plus 1. Easy to count. These sums are easy to count. If there are k summand equal to 2, there must be n minus 2k summand equal to 1. And there are n minus 2k plus k, choose k, which equals n minus k choose k, ways of ordering the summands. Therefore, a sub n is going to be equal to the following. Take k from 0 to n over 2 floor of n minus k over k, n minus k choose k, which is n choose 0 plus n minus 1 choose 1 plus n minus 2 choose 2, etc. This is a pretty good answer, and it's certainly an explicit formula. It may be used to compute a sub n directly for small values of n. It does have two drawbacks. Aesthetically, it is certainly not as satisfactory as 2 to the n. In practice, it is also not as useful as it seems. After computing a few examples, we'll soon notice that computing binomial coefficients is a non-trivial task. I mean, hey, if you need some binomial coefficients calculated, you know who to talk to. In fact, there is a more efficient method of computing a sub n. Let n be greater than or equal to 2. In domino tiling, the leftmost column of a 2 by n can be covered by a vertical domino or by 2 horizontal dominoes. If the leftmost domino is vertical, the rest of the dominoes tile a 2 by n minus 1 rectangle. So there are a sub n minus 1 such tilings. On the other hand, if the 2 leftmost dominoes are horizontal, the rest of the dominoes tile a 2 by n minus 2 rectangle. So there are a sub n minus 2 such tilings. We obtain the recurrence relationship. A sub 0 equals 1, a sub 1 equals 1, a sub n is equal to a sub n minus 1 plus a sub n minus 2. Which allows us to compute every term in the sequence in terms of the previous ones. We see that a sub n equals capital F sub n plus 1 is the n plus 1th Fibonacci number. This recursive answer is not as nice as 2 to the n either. It's not even an explicit formula for a sub n. If we want to use it to compute a sub n, we need to compute all the first n terms of the sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. However, we can compute those very quickly. We only need to perform n minus 1 additions. This is an extremely efficient method for computing a sub n. There's a well-established method that turns linear recurrence relations with constant coefficients, such as 1.2, into explicit formulas. We'll review it in theorem 1.3.5. In this case, we get a sub n equals 1 over root 5 times the quantity 1 plus root 5 over 2 raised to the m plus 1 minus 1 minus root 5 over 2 raised to the m plus 1. This is clearly the simplest possible explicit formula for a sub n in the sense that it is a great formula. The drawback is that this formula is not very useful if we want to compute the exact value of, say, a sub 1000. It is not even clear why 1.3 produces an integer. And to get it to produce the correct integer would require arithmetic calculations with extremely high precision. An advantage is that, unlike 1.1, 1.3 tells us very precisely how a sub n grows with n. Asymptotic formula. It follows immediately from 1.3 that a sub n is equal to c times phi to the n, where c is 1 plus square root of 5 over 2 root 5, and phi is equal to 1 plus root 5 all over 2. This notation means that the limit as n approaches infinity of a sub n over c times phi to the n equals 1. And in fact, since 1 minus root 5 all over 2 is less than 1, a sub n is the closest integer to c times phi to the n. Generating function. The last kind of answer we discuss is the generating function. This is perhaps the strangest kind of answer, but is often the most powerful. Consider the infinite power series a sub x equals a sub 0 plus a sub 1 x plus a sub 2 x squared, etc. We call this generating function of the sequence a0, a1, a2, etc. We now compute this power series. From 1.2, we obtain that a sub x is equal to 1 plus x plus the sum as n is greater than or equal to 2 of a sub n minus 1 plus a sub n minus 2 times x to the n times x to the n is equal to 1 plus x times the quantity a sub x minus 1 plus x squared a of x, which implies a of x is a sub 0 plus a sub 1 x plus a sub 2 x squared, etc. equals 1 over 1 minus x squared. With a bit of theory and practice, we'll be able to write the equation 1.5 immediately with no further computations. To show this is an excellent answer, let us use it to derive all other answers and more. Generating functions can help explicit formulas. For instance, rewriting a sub x equals 1 over 1 minus parentheses x squared, x plus x squared, is the sum as k is going from 0 to infinity of x plus x squared all raised to the k. Rewriting that, we recover 1.1. If instead we use the method of partial fractions, we get these things all over again, which brings us to our second explicit formula. Generating functions help us obtain recursive formulas. In this example, we simply coordinate the coefficients of x to the n on both sides of the equation. A sub x times the quantity 1 minus x squared is equal to 1. And we get the recurrence relation 1.2. For a moment, let us not worry about where this series converges. The issue of convergence can be easily avoided, as combinatorialists often do. in a way that will be explained in 1.3.1 or resolved and exploited to our advantage. Let us postpone that discussion for the moment. Generating functions help us obtain asymptotic formulas. In this example, 1.5 leads to 1.3, which gives 1.4. In general, almost everything we know about the rare growth rate of combinatorial sequences comes from their generating functions, because analysis tells us that the asymptotic behavior of a sub n is intimately tied to the singularities of the function a of x. Generating functions help us enumerate our combinatorial objects in more detail and understand some of their statistical properties. For instance, we want to compute the number a sub mn of domino tilings of a 2 by n rectangle that we use exactly m vertical tiles. Once we really understand in section 1.3.2, we will get to the answer immediately. Suppose we wish to know what fraction of tiles is vertical in a large random tiling. Among all the a sub n domino tilings of the 2 by n rectangle, there are some as m goes from 0 of m times a sub mn vertical dominoes. We compute. Right, sum as n goes from 0 of the sum as m goes to 0 of m times a sub mn times x to the n. Partial fractions then tell us that the sum as m goes from 0 of m times a sub mn is approximately n over 5 times phi raised to the m plus 1. Roughly speaking, about 1 in approximately 1 over root 5 times n times a sub n. So what's a good answer to an enumerative problem? Not surprisingly, there is no definitive answer to this question. When we count a family of combinatorial objects, we look for explicit formulas, recursive formulas, asymptotic formulas, and generating functions. They're all useful. Generating functions are the most powerful framework we have to relate these different kinds of answers and ideally find them all. Okay. You know what? I want to come back to this. We can read through 20 pages. That's reasonable. We're almost halfway already. All right, we'll come back. All right, so as I said before, took a math history class as part of the math education major at the University of New Hampshire, and Kenneth Appel came and taught a class for us while our usual teacher was out for the day. And we got to listen to his lecture on how computer-generated proofs worked and the controversy that existed in the 1970s and all sorts of stuff. So it's a very nice little sorry, just practicing some stance while I'm doing this, because quite frankly I need to move the blood. So, Mathematicians' Attitudes Towards Computer Proofs by Kenneth Appel. I'm also going to put in, this is the that one. And next up is right. So this is based on talks that were given at Universidad de Navarra and Universidad Público de Seville in April and May 2003. Controversy surrounding the acceptability of proof of the four-color theorem in 1976 led me, Kenneth Appel, to think about the general question of the attitudes of mathematicians toward proof, and more specifically on proofs that involve machine computations that cannot reasonably be checked by a mathematician working without a computer in an essential way. I do not claim expertise in this area, but would like to express my views on the situation. In order to discuss what can be accepted as proof, it seems easiest to start with a short discussion on what mathematicians seem to agree cannot be accepted. We'll use the term argument for something that has a structure of a proof, but may or may not be a correct proof. An argument that is not a proof of what it is purported to be is called unacceptable. We assume that we're using a sound proof system. This means that no formally correct argument can be used to prove anything that is not true in the intended model. Then I think it is generally agreed that an argument is unacceptable if a counterexample to what is claimed to have been proved can be found. Furthermore, an argument is unacceptable if an argument with essentially the same reasoning is unacceptable. The second argument may claim to prove something different. The third reason for an argument to be unacceptable is more difficult to define. We'll start by introducing a term which, to the best of my knowledge, was first used by Hyman Bass. The grain size of a proof is the largest size of a step that is used in a proof. Thus, in a paper written for specialists, a much larger grain size might be permitted than a proof written for an undergraduate examination. The fact that grain size seems significant is an indication that the proof has a role in communication, which is in many ways as important to its role in verification. but this very fact makes the next concept rather imprecise. An argument is unacceptable if it has a gap. By a gap, we mean a step whose correctness cannot be demonstrated by the proposer to the intended audience. This is a very vague concept, and in the past, some correct proofs had not initially been accepted because of supposed gaps that were later shown to be non-existent. One of the most thoughtful analyses of the situation was published by Tomaszko in the Journal of Philosophy in 1979. He argued that while the argument in papers every planar map is four-colorable by Appel, Haken, and Koch very probably showed that the statement in the title is true, it did not satisfy the conditions that were required for a proof in mathematics. He argued that accepted criteria for the proof of mathematics were 1. The proof is convincing, 2. The proof is surveyable, and 3. The proof is formalizable. There is no question in my mind that mathematicians wished that this was true of every proof so that they were willing to accept. But looking at mathematical journals, this list of requirements seems a bit optimistic. It is certainly desirable that proofs be convincing, but as will be shown by examples, it is certainly not the case that all arguments that have convinced referees and editors that they should be published have actually been correct. If we ask that proofs be surveyable in the sense that a proof can be read and checked by a single mathematician or small group of mathematicians in a reasonable length of time, then we really should define a reasonable length of time. The wish that proof be formalizable is a very reasonable one, but in the cases of most complicated proofs, there has never been any attempt to verify formalizability. In any event, the requirement of surveyability without the aid of computers would not only rule out the proof of the four-color theorem, but also more recent work like classification of finite groups and the solution of sphere packing problem. To my point of view, Tomaszko took a rather idealized view of mathematicians' attitudes toward proof. I believe the controversy about whether to accept the proof of the four-color theorem was based on other questions. I think that every mathematician, as well as every scientist or engineer who thinks about proofs, would want proofs to verify the correctness of the statements that they are purported to prove. But for mathematicians, proofs are much more. They are the art forms in the sense that most mathematicians would agree on whether a proof is beautiful or not. Indeed, Ardila imagined God's book in which the most beautiful proof of every theorem was inscribed. I think mathematicians hope that proofs of important theorems, whether or not they qualify for inclusion in the book, are aesthetically satisfying. I think that mathematicians believe that proofs should help one understand why the statements they claim to prove are true. Bourbaki made an implicitly even stronger demand on the interaction of mathematicians with proofs. He said, quote, "Indeed, every mathematician knows that a proof has not been understood if one does nothing more than verify step by step the correctness and deductions of which it is and has not tried to gain a clear insight into the ideas which have led to the construction of this particular chain of deductions in preference to every other one." Reminder that Bourbaki was not a real person, however, was a group of people and has been around for quite a while in French mathematics. I would like to interject a couple of examples of proofs that most mathematicians I have talked to recently consider aesthetically pleasing. The first is the classical proof that root 2 is irrational. It runs through this whole thing, and we've done it before. So basically, you claim that you suppose that the square root of 2 is rational and therefore can be expressed as the ratio of two integers. And by supposing that because it's in a lowest form already, we're not going to have any particular simplification of this fraction. Then if you right, okay. If any integer whose square is even must itself be even is a necessary lemma that needs to be used throughout throughout this one. So we suppose that root 2 is rational and can be expressed as p over q in lowest terms. Then when squaring, we end up with p squared over q squared equals 2, and therefore p squared equals 2q squared. So now p, or p squared, has been expressed as 2 times q squared, which is an integer. So 2 times an integer is an even number. And similarly, by saying, oh, well, if p has to be an even number, then what happens when we end up squaring it? Well, if p is even and then we square 2m, where m is just some integer, replace p with that, then when we square it, we end up with a whole bunch of stuff, which then says that, oh, by the way, your q also has to be even. So if p is even and q is even, now it's not a it is not a simplified fraction. So that's a small problem there. The second proof that I had not seen until recently, though I am sure it must have been known to Hilbert, that is a short, non-constructive proof that there are irrationals x and y such that x to the y is rational. Right, so lemma. First note that the square root of 2 raised to the square root of 2, all raised to the square root of 2, is going to be root 2 to the second power, or just 2. So there is at least one number where you have an irrational that's raised to another irrational that ends up with a rational number. Well, no, actually, that's not quite true. An irrational raised to an irrational, and then all of that raised to another irrational, ended up with irrational. Okay, so suppose root 2 raised to the root 2 is rational. Then letting each of x and y be square root of 2, we have found such a pair. Right, so here we just kind of assume the one case, right? Assume that root 2 to the root 2 is rational, and in that case, then we took that thing raised to the root 2. So a rational raised to an irrational, and then we got another rational. That's, no, not quite. Sorry. Root 2 to the root 2. If it is rational, then so proved. We're done. However, if it is irrational, then we let x be root 2 to the root 2. And then we let y be root 2. So, because we did root 2 to the root 2, all raised to the root 2, now we can corner this particular property and say that, okay, look, either root 2 to the root 2 is rational, in which case we're done. Or we say, okay, root 2 to the root 2 is irrational, but if we raise it to another root 2, then those exponents multiply together to become just 2, and our root 2 now gets squared, which becomes rational. So we have, in effect, cornered the property by saying, look, either this thing is rational or irrational. There's only one possibility of those two. Right? So rational and irrational really just corners the market on on all this. Or sorry, jeez, corners the market. It partitions all these numbers. So either a number is going to be rational or irrational. There's no third option here. You can't be anything else. Either you can be expressed as as a number. You could be expressed as the ratio of two integers, or you cannot be expressed as the ratio of two integers. So it's going to be one case or the other. We don't know which one it is, but again, we can say with absolute certainty that this thing, root 2 to the root 2, all raised to the root 2, will show us that some amount of irrational to an irrational is going to get us a rational. One might note that although this elementary argument leaves one uncertain as to which of the two potential examples really satisfies the condition, and thus clearly is non-constructive, it follows from Hilbert's not nearly so elementary proof that root 2 to the root 2 is irrational, that the second example is the genuine one. Right. We're going to take a 3-minute break for ads. We shall return. Hope you all are having a good day, and like I said, we'll be right back. Thank you so much for stopping in, and we will continue the rest of the Appel paper here when we get back. All right, thanks everybody. Welcome back. All right, in the world of computer proofs, two types of proofs have been discovered using computers. We'll call them benign and non-scannable. Proof will be called benign if it can be rewritten in standard form. There has never seemed to be serious controversy about use of any methods to deliver an argument as long as it can be formalized by standard methods. Landers and Parkin, 1967, used a computer to look for a counterexample to a conjecture of Euler that it was impossible to find a fifth power that was a non-trivial sum of fifth powers. Singular moduli. Good evening. Erhard theory. Used it in a permutation study at one point. Permutahedron. Okay. A computer program produced the counterexample 144 to the fifth is equal to 133 to the fifth plus 110 to the fifth plus 84 to the fifth plus 27 to the fifth. The result is obviously checkable by hand. A proof will be called non-scannable if it is impossible for a single human being to check all of the details within a reasonable length of time, where reasonable indicates an upper bound of the maximal verifiable human lifetime, but practically means a time considerably less than that. A rather less than serious analysis of this phenomenon may be found at the website improb.com and a bunch of stuff. What follows is one of 800 similar computations that form part of the shortest known proof of the four-color theorem due to Robertson Seymour et al. 1993, which is a considerable simplification of the original proof, Appel, Haken, and Koch 1976. Let's see if this website still exists. Probably not. Nah. Not really surprising. Wayback Machine? 4-color-36-1.html. Phew. Wow. Somebody looked for it in 2024. But mainly, it was in use in 2005, 2006. Wow. Okay. Let's do it. All right. Classical gas. Proofreaders update. January 1990. Four-color map theorem. Joe Slavsky, Newark, New Jersey. In 1976, Kenneth Appel and Wolfgang Haken, University of Illinois, solved the four-color theorem. Among mathematicians, the proof was met with both jubilation at the solution of the problem that had defied solution since Francis Guthrie posed it in 1852, and dismay. Many mathematicians were troubled because the proof made unprecedented use of computer computation. It was feared that the correctness of the proof could not be checked without the aid of a computer. Tonight, by the way, we have the Badger Master Stout coffee stout, which I'm questioning the wisdom of this, given that it is 11:30. Eh. It's quite nice. I don't know why it was on discount. Classical gas. Ah. Well, anyway. I will save that for later. Four-color theorem is one of the few great mathematical problems that even a non-mathematician would appreciate. Yeah. So yes, you're trying to color all of the maps on a particular, map. Just pretend for a moment that they're real countries that are all laid out next to each other. How many colors would you need in order to color the entire map such that all of the all of the countries that are adjacent to each other are different colors? So never two countries that share the same color next to each other. And so, like I said here, Ken Appel ended up proving with Wolfgang Haken that 4 is all you need. In 1982, together with my fellow members of the American Society of Proofreaders, took up the task of checking Appel and Haken's proof using only traditional means. Our work is funded by the U.S. government's Strategic Defense Advanced Research Project, DARPA anyway, projects agency, Each January, we issue a brief public statement about our progress. This is the 6th such report. 3 members of the proofreading team died during calendar year 1989, reducing our total number to 117. It was decided to reduce the standard proofreading work week to 10 hours per day, 6 days per week. This measure was effected primarily due to cost restraints newly imposed by the funding agency. This year, 43 person years were expended in preparatory computation related to semi-critical open subsets of phi 6 that satisfy the bend condition. I don't know what that is. This is the sort of task that we, and presumably Appel, wouldn't ordinarily delegate to troublesome graduate students. However, the overarching importance of this proof precludes us from delegating any portion of it, no matter how straightforward, to unproven personnel. The preponderance of proofreading time, as in previous years, was devoted to iterative and/or recursive computation related to the introductory portions of the proof, outlined in our annual statement released January 1983. The nature and importance of the task at all times is paramount in our thoughts. This is an exhaustive proof. And that last bit there is really the important thing, that it was, in fact, I believe he set it up in terms of graph theory. So he show that all of the different types of graphs that you can create are going to end up only with individual nodes, which can be colored in one of 4 colors. Nope. All right. Consider the graph in diagram 1. I don't have a diagram 1. Cool. This is the graph of a 13-ring configuration. The circuit of numbered vertices that form the boundary of the graph is called the ring. Suppose the vertices of this graph were colored with 4 colors, call them 0, 1, 2, 3, in such a way that no pair of edge-adjacent vertices have the same color. Then, since renaming the colors does not essentially change the coloring, we could assume that the vertex marked 1 is colored with a 0, and the vertex marked 2 is colored with a 1, etc. Proceeding clockwise around the ring, no vertex is colored with a 3 unless a preceding vertex has been colored with a 2. There are 65,531 such colorings. Now I believe 65,532 is a multiple of 2, or is a power of 2. 65,532. We need log base 2. Boo. Nope. It's really close to 16 though. What is 2 to the 16? 65,536. So that's 5 short. It's interesting. Some of these colorings are such that they arise from a forecoloring of the entire graph. These are called initially good colorings. It is routine to determine whether a coloring is initially good. Try to color the remaining 10 vertices with no adjacent pair having the same color. There are many fewer than 4 to the 10th colorings to try. Each one either works or does not. If one such coloring of the remaining vertices works, the coloring of the ring is usually good, is initially good. If not, the coloring of the ring is not initially good. At least 500 of the configurations used by Robertson et al. Had ring size 13. The first step in dealing with each such configuration was to find the initially good colorings. The rest of the computations are somewhat more complex, but none are beyond the ability of a very patient and accurate high school student to perform. Work on formal verification of computer programs leaves the possibility that a program that generates a non-scannable proof can be proved to be correct, but to the best of my knowledge, no such program has yet been verified. This is, again, 1993, I think, 2003. 2003. The probability of hardware failure is not zero, but with current computers, if a result is obtained more than once by either a verifiable program or distinct computers using different programs, it would appear to have a high enough probability of correctness to be much more likely to be correct than would the average published proof. I would argue that the question of acceptability of proofs has been idealized and is much more of an emotional issue than a pragmatic examination of a difficult question. Mathematicians have not, in previous times, had to face the fact that there will be theorems with proofs that are not surveyable in the sense that they are used to. But this could have been interfered from the work of logicians in the 1930s, in particular from Church's theorem. Originally, this theorem stated in the language of Church's calculus of lambda conversion. Theorem 19, there is no recursive function of two formulas A and B whose value is 2 or 1, according as A convert B or not. Immediately after proving the theorem, Church points out that if the Entscheidungsproblem, decision problem, for the system were solved, it would be a means of determining effectively of every proposition psi of AB whether it was provable, and hence a means of determining effectively of every pair of formulas A and B whether A convert B, contrary to Theorem 19. In particular, if the system of Principia Mathematica be omega consistent, its Entscheidungsproblem is unsolvable. Why is this relevant to our discussion? In particular, if one were using the system of Principia Mathematica and were able to bound the length of the shortest proof of every provable formula by any recursive function of the length of the formula, then the Entscheidungsproblem of Principia Mathematica would be solvable. Thus, at least in the system of Principia Mathematica, there must be theorems with proofs that are long with respect to the lengths of their statements. Note there is no way to determine a lower bound on the lengths of such statements, and so Church's theorem does not necessarily imply that there must be some theorem whose statement is less than 10 to the 10 symbols that requires a long proof. However, Church's theorem makes it clear it is not reasonable without further information to assume that if a theorem is provable, it must be provable in a manner that satisfies our former definitions of surveyability. A significant question is whether one can ever seriously examine the attitudes of mathematicians toward computer proofs by just examining the questions discussed above. Very few mathematicians really think very much about the nature of proof. Most mathematicians are involved in a particular branch of mathematics and communicate their discoveries and ideas to other specialists in papers and in journals. Often they have insights that, while basically correct, are not fully communicated in these papers. It has often been said, obviously with considerable exaggeration, that the great topologist Solomon Lefschetz, he never stated an incorrect theorem and never provided a correct proof. The great probabilist J.L. Doob has said, quote, "If a fountain pen is held 6 feet above an open mathematical journal and a drop of ink is released, with probability 1/2, it will land on an error." A few of the more famous erroneous papers will be discussed below. First, one might consider Arthur Kemp's proof of the four-color theorem, published in the American Journal of Mathematics in 1879. The paper was obviously refereed quite carefully by the editor of the journal, Joseph Story, for Story wrote a long note in the same issue of the journal pointing out all of the errors he had found in the exposition, none of which were serious, and completely missed the fact that the proof itself was fallacious. As shown in the 1890 paper of Percy Heawood. A second example involved Dane's lemma. Dane's lemma states that if you have an embedding of a 1 sphere in a 3 manifold which consists continuously over a 2 disk, then it also extends over the disk as an embedding. It was conjectured by Dane in 1910. Proof, quote-unquote, was given by Knesse in 1928, but work of Lefschetz in 1937 showed that this proof was not correct. Finally, a correct proof was supplied by Papakyriakopoulos in 1955. It's quite a long name. A well-known, relatively recent example of difficulties in examining proofs is described by Lipton, Perlis, and DeMilo, who wrote in 1976, "Recently, 2 independent groups of topologists, one American, the other Japanese, announced results concerning the same homotopy group, a type of object arising in the homotopy theory. The results turned out to be contradictory since both proofs were very complex and involved detailed symbolic and numerical calculations. It was not at all evident who had goofed, but the stakes were sufficiently high to press the issue, so the Japanese and the Americans were exchanged. Obviously, each group was highly motivated to discover the error in the other's proof, but neither the Japanese nor American team's proofs could be discredited. Yet one was clearly incorrect. Subsequently, a third group of researchers obtained yet another proof, and this time supporting the Americans. The weight of evidence now being against their proof, the Japanese team retired to consider the issue. Notice the probable truth of the theorem at this point is still very low compared to the far more comprehensible results we tend to regard as theorems. One of the American mathematicians was so unsettled by this experience, He has since given up on mathematics for, presumably, a career in which the results of his labor can be judged more objectively. In 1976, the reaction to the proof of the four-color theorem by many mathematicians was certainly influenced by their relative lack of familiarity with computers and the fact that no previous conjecture of such prominence had ever claimed to be proved in a non-scannable manner. Mathematicians have always taken great pride in the feeling that they fully understand the proofs of the results on which their own work depended, even though they had, by the 20th century, realized that even the greatest of their contemporaries could not claim familiarity in depth with all known mathematics. Something that might be reasonably claimed for comparable mathematicians at the beginning of the 19th century. Very true. This is one of those, like, if I were to go back in time, I might be able to invent stuff. But realistically, that's pretty much the only way that I would be able to invent stuff is, going back in time and finding whatever the cutting edge of mathematics is at that particular time, and then remembering something from our time, The discipline was clearly changing. In the summer of 1977, Armin Haken, the oldest son of Wolfgang Haken, was a mathematics graduate student at the University of California, Berkeley. Since he was familiar with the four-color proof, he was asked to give a lecture on the subject. He reported that when he concluded his talk, the audience split into two groups. The first, largely those in the audience over the age of 40, felt strongly that no computer proof should be accepted. The second, and younger, group felt that the proof included 700 pages. Since the proof included 700 pages of hand checking, mainly of the discharging procedure, it was much too complicated to be trusted. In the quarter century since 1976, a number of non-scannable arguments have been used in work central to mathematics. As part of the huge effort involved in the classification of finite groups, it was necessary to use computers to examine some of the properties of the largest sporadic simple groups. It appears that mathematicians have largely believed that the classification was successful and believed the results. In 1989, Lam, Thiel, and Svaet announced a non-scannable proof that there are no projective planes of order 10. In 1997, Robertson, Seymour, Sanders, and Thomas published a considerably simpler non-scannable proof of the four-color theorem. In 1998, Thomas Hales announced that a non-scannable proof of Kepler's conjecture on sphere packing in an article in Nature published in July 2003, several months after the lectures on which this article was based, George Spiro reported in Nature on something that give some indication of the current generation of mathematicians on non-scannable proofs. Robert McPherson, an editor of the Annals and a number of the and member of the Institute for Advanced Study, invited Hales to submit his paper to the Kepler conjecture on the Kepler conjecture to the Annals of Mathematics. McPherson appointed an unusually large group of 10 distinguished referees who spent the considerable time examining the proof. While they could find no errors in the proof, they announced that they could not examine the computer code to sufficient detail to verify that it was correct. Thus, the paper will appear in the journal with the caveat that the proof was impossible to fully check. Pierre Deligne, certainly one of the great mathematicians of our time, was quoted in the article as not believing in computer-aided proofs and saying, "I'll believe in a proof when I understand it." While few mathematicians have the ability to understand proofs as well as Professor Deligne does, it is not unreasonable to believe that the word understand will eventually be viewed more broadly and that the non-scannable proofs will not only be published but fully accepted by most mathematicians. I don't know, what do you think? Do we make it? Do most mathematicians now accept computer-based proofs? In the case of Appel, it was a proof by exhaustion. So they found the basic structures of all possible graphs, which were equivalent to the four-color theorem anyway, it was the maps were equivalent to the four-color theorem, and they checked not literally every different arrangement, but they broke them into families and said, like, anything that has this particular family is just going to be out because if the exemplar, right, if the parent type didn't meet the criteria, then the child version or the larger map, which has the same outcome, which has the same shape to it, is also not going to be something that we have to worry about. Okay. Let's head on over to Zach's. Zach is currently on. He's only been on for an hour, so that'll work for us. Really? But why? ¿Por qué? But I would like to raid Zach. Jerks. Fine. Can't raid Zach, apparently. Been on a long time, but we'll go see Rhacodactylus, maybe? Yeah. Okay. We'll be back tomorrow with probably back to math calculations, just to get us back on schedule. And I'm going to be working on my TTRPG stuff on Thursday. I need to type up all of everybody's stories, so I might start doing that like tonight or tomorrow and see where that takes me. So, hope you all have a good night. My name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.